Okay, well, you know what? Better late than never. I know I was going to do this earlier today, but things came up. Sorry, you know how it goes. We are going to do this a little bit later tonight. It's 6 o'clock my time, but we are going to make this happen. So people have asked me to kind of do a little bit more math presentations like I did on the other channel, the Great Debate Community channel. And one of the things that have come up is summations, because people look at these symbols and they go, what the hell does this shit mean? So I decided to kind of do a little basic presentation on it. And I brought two experts in to kind of help me, because it's been a very long time since I've actually really done anything with summation. So I brought my good friend Landon Curtinol, supporter of the channel, Patreon, and computer scientist, astronomer, mathematician expert, dude.
And good morning, good afternoon, or good evening, depending upon your time zone and latitude. And I hope you got your plus signs already lined up for the show.
This is going to be fun. And if you guys may know us, I bought this beautiful human specimen of a person here. I think it's okay if I tell him that he's a smart math dude. He's working towards his PhDs. I can say that. You're
Yeah,
a smart guy. Okay.
I'm happy with that.
All right. And I'm not going to say where, but Jonathan is a friend of mine from Facebook, and I've known him quite some time. We've discussed math for ages, and I've kind of hoped to get his channel started going. He has a channel called Epic Math Time. If you guys haven't checked it out, it's awesome. He's got a lot of effort into it, and he knows what the hell he's talking about. So that's a rare combination when you have a new channel. So Jonathan, welcome. I've been trying to get you in here forever because
sorry about that.
Good. I know you've been busy, dude. I get it.
Yeah.
Well, you want to tell me about your channel real quick? What you kind of
sure. So basically, I'm really using it to do whatever I want right now. But I've tackled a few questions that I found interesting when I was in undergrad. I plan on doing some lessons for the classes I teach. I've done a couple of those already, but that's really my main motivation right now. But yeah, I have a lot of future plans for it. I'm pretty happy about it. So.
Let me actually stop screen sharing so people can actually see who you are. I didn't realize there was screen sharing, and that would be take away from the whole effect that you've got going on with the soundproofing and you're going all out on your studio stuff.
Yeah, so the soundproofing, it's mainly so that I have a nice contrast for that white marker, and any sound cancellation or whatever it gives me, that's just like an added benefit. Yeah.
I'm actually going to be doing something similar in the next week or so. I've actually got soundproofing material, and I'm going to be rearranging my little office here a little bit, which is my room, to make it a little bit more soundproof. We put a heavier door in because my roommates can hear everything through this last door I had. It was so thin. So we got a solid wooden door, and now I'm going to try to soundproof it so I can do things like this a little bit more later in the night. So anyways, before we jump into this, I just have a real quick question for Landon. Landon, tell everybody, if you can, a little bit about Comet 46P, where to see it. If you've seen it, have you watched it? Is it a visible magnitude yet?
So Comet 46P, and the P designated as a periodic comet. And you say, well, aren't all comets periodic? Well, actually, no. Some of them are actually hyperbolic, and some of them come by the sun and leave and never to return. But 47P is one of those periodic comets. You probably know the most famous one, Halley's, which has designated
76 years.
Is a nice periodic comet. So this was the 47th comet whose period was determined, and this particular time is going past the Earth in a nice, relatively close. By close meaning something on the order of around 7 million kilometers, I think. And that's pretty close on a cosmic scale.
I'd say so.
And the flyby, the close period is sort of now. And the best way to find it is to go to skyandtelescope.com, where you will find that they have nice finder charts, and you can find it there somewhere between the Pleiades and Orion. Currently, it's somewhere in that vicinity. But go find the finder chart there. It is it's not a blazing comet as in like you go outside and see this long giant tail. This is not a Comet West, but it does show up nicely in binoculars, and it's worth looking for. It doesn't look like the pictures, because the pictures you see are long exposures by big telescopes, but it's a nice fuzzy spot in the sky. I wasn't really able to see much of a tail there, but other long exposures can see a bit of a tail on it.
It's a little bit roundish. Yeah, I looked. I haven't seen it yet. I've just looked at the photographs. It's near Pleiades and Taurus. I think I'm wondering if Stellarium would actually be really good to try to find it easier. I
Yeah.
think you can download the data for that. But anyways, yeah, I was just kind of curious. It's about 3.9 magnitude, I guess, or will be,
And
which is
that's you
visible.
know, it's certainly you're not going to see it in naked eye in the city. Out in the country,
Yeah, you're gonna have
you
to go
would
to a
see
clear
it as
sky.
kind of a little, a fuzzy cotton ball up there in the sky.
That's what Comet Hale-Bopp looked like back in the
Oh,
90s. It was just a little blob. But anyways, let's get started on this.
yeah.
Hopefully we won't get too many dislikes. I know this is math. Some people really like math, some people don't. I'm not a big fan of math, but I've had to use it, so that's why I have mathematicians in here. So we're going to just jump right into this, and hopefully as we go, they can kind of guide it and tell me where I'm wrong and correct me. So hopefully by the end of this, you have correct information. So this is actually Calc level 1. It's math 123, I guess, when I kind of looked into it and what level it's at. Um, it's going to be dealing with summations and this little symbol here. And so I'm just going to kind of go through this, what I wrote. I wrote all this. And
You need to show the screen.
oh, I need to show the screen. That would help, right? You think I would figure this shit out by now, right?
There you
All
go.
right. Here's my, okay. So I wrote all this. So what I wanted to do is when I learned about summations, I thought it was a little bit more complicated than what it was. And I overthink things, right? And I didn't like the way it's being explained. So just like every other math thing I've done, I've tried to relate things in a way. How would I have better learned this when I was going through it, right? And I think Jonathan, when he teaches math, because he teaches math, when I watch his videos, he does a lot of the same types of presentation things that I would like to have had years ago. So, Jonathan, when you do your presentation, is that the one thing you have in mind to the person listening, to your students like that? Is like, are they understanding this conceptually?
Sorry, we're not
You
hearing the
muted.
audio.
You lost your audio. Loss of audio casually.
So,
Uh-oh, he
one
broke it
thing
again.
I should mention, by the way, Steve, is that's a very famous thing to do, right? When you learn something, one of the best ways to learn it is to understand it to a level where you can teach it, particularly to someone who is not steeped in the nomenclature, and to explain it without using terms of art.
And you know what? I'm
To
flattered
be
by
able to
that. 'Cause
explain it to a kid.
yeah, you knew. I mean, you knew Feynman, so I mean, that coming from you even actually is amazing because Feynman was one of my heroes as far as just pure brilliance in a bottle kind of thing. You know, if you could just bottle up his genius and sell it. Oh, I think Jonathan collapsed. I think we had a wave function collapse of Jonathan. Oh no, it's still muted.
Yeah,
It was
he
working
was.
fine a second ago, dude.
Yes.
Oh, technological issues. Nope. The outside feed can't see it, but I'll show you guys here. He's just mouthing things, but we can't see anything or hear anything. There we go.
Okay, here's the thing. Apparently, I can either hear or speak, but not both at once. We'll make do though.
That's bizarre.
So you can hear me now.
Yes, can you hear us?
Yeah, I can.
Okay.
Is audio okay?
Yeah. All right. So
All
why?
right, good.
So
Good. I
so
think we're
you can
good
answer
then.
my question now. For
Yeah.
your students, how do you go about making sure that they understand the concepts?
Yeah. So one thing I think that I do pretty well is that I still have a sort of like academic empathy. So like I still remember what about those concepts that I'm teaching I thought was hard to come, to grasp. So I think, there's this tendency to say like everything that you've already learned is easy, to have this, smugness. So like I can still identify what I think was challenging about it and kind of like tackle the issues that I think are going to cause people the most trouble. And I think I have a unique way of understanding things. And I try to like read from the students to make sure that it's actually effective. And if it's not, I just change what I'm doing.
Yeah, I think that's a great approach. Somebody says in the live chat, Green's theorem and Maclaurin series. That next episode, I already did Maclaurin. Well, I did Taylor series, which is just a Maclaurin series, special type of Maclaurin series. So I've already done Taylor series. Go look at it. Matter of fact, that was actually one of my, I gotta admit, one of my better presentations. I thought.
Yeah.
So
But you say why do we have symbols like this in mathematics?
to confuse
And
people.
and the answer really is that to be able to express concepts in a precise manner. Unlike, let's say, philosophy, where you can spend half an hour just arguing over the first use of the first term. In mathematics, there are well defined symbols that allow you to bring forward concepts. because the English language or whatever language you speak is not really a concise nor precise way to describe what mathematics is trying to describe.
Yeah, I think there's a boundary for linguistics in general. Like even in logic, you can translate many things linguistically into one type of logic, but logic only translates linguistically one way. It's very precise.
Yeah.
So there's no ambiguity when it comes to logic, although there's many different ways semantically you can convert from linguistics to logic.
And mathematical logic is again very concise. You don't have the kind of long arguments in a mathematical logic class that you might have in a philosophical logic class.
Right. All right. So let's dive into this. So sigma, this little symbol here, Greek for, I believe, S, represents a summation, the addition of a sequence of numbers. And very, very basic, a sequence of numbers is just what I have here, 1 plus 2 plus 3, anything like that, which is a list, an ordered list, or if you're British, a progression. Actually, that's not a summation, a sequence. That's actually a sum, but a sequence is any kind of ordered list. So if I have the bracket 1, 2, 3, that's an ordered list. If I want to take the summation of that sequence, and I did a separate presentation a while back on the difference between sequences and summations, dealing with 0.9 and repeating. Matter of fact, Landon actually helped me in one of those. That the summation of the sequence is equal to the sum of the value of the sequence. And all that fancy way of saying is that if I add up to those numbers, what is the sum? If you guys remember from a previous presentation, we talked about the limit of a sequence. We talked about what something converges upon. And I wanted to get another video separate for that. So I'm not going to get into some of the technical stuff of what it means to have a convergence, what it means to have a sequence converge, or how you test for it, like a geometric series progression or geometric test, or different ways of testing for convergence. I'm going to do a separate video on that, if that's okay. But at this video, I just want to focus on what it means to do a summation if you see this symbol. So when you see the symbol, it's usually given by what's called an index. And an index is basically telling you from what range, from lower to higher, to take the summation. It's symbolized by here. If you look, does it show my mouse? Yeah. So here I'm using
the index is the value that varies.
Yeah. These are value numbers that can change. A to B, usually those are constants, right? A and B typically are constants. But here, this is what I hate about mathematics. You got to know which thing you're dealing with, because like usually like A and B would be considered to be constants, X, Y are variables. But in this particular case, these indexes, they do change. They're not constant values. You can make them anything you want. So in that case, they can hold any value. But they are a bound between what I want to start a summation at and finish a summation at. So they're called a lower bound and upper bound. N typically is what's called the add-in, summand, or I call it argument. Because I'm used to using functional notation. And in functions, the argument is what you send to the function in order for it to do something and get a result out. So I'm always using the term argument. Do you guys have a preference? Jonathan, what do you use?
Well, I would say in this particular case, the argument would actually be A and B. Yes. Viewing this as a function. Sorry, go ahead.
No, yeah, you're right. You're right. Yes.
I would say viewing this as a function, it's the function that takes the sum of all the integers from A to B. So the input there is A and B. So,
the index in this particular case is N, not A and B.
See, I thought that as well, but when I've looked into this, the N would be a subscript A or subscript B here, where that would be the index, and the argument is this N. Now, you know what? I'm gonna have to look at that, because
have you heard the term dummy variable before?
Yeah, of course.
That's sort of how N is being used.
I look at the dummy variable as more AK. A would be if you have A sub K or A sub I. A is those are usually your dummy variables. K can be any arbitrary variable. Yeah, this is where math gets fun, right? All right. Well.
Anyways, I posted a link there for another one that talks about the notation. And again, it's what varies. What does So the summation is N varying over the range. So A and B is the range of N.
Okay, let's go with that. So N is going to be equal to some range with lower bound of A and upper bound of B. And this will start making sense in a second.
By the way, those are inclusive, right?
Yes.
It starts with A and ends with B.
Yeah. Instead of being in between them, they're inclusive. And normally when you have a range, you use block parentheses for if you're including the outside of the range, and open parentheses if they're not included, right? Um, one of the key takeaways that I do get later on is that don't get focused on the letters that much, because these letters can be numerous. You can see N being A, you can see AB using N and M. You can see many different types of letters used for things. They all basically mean the same thing. However, there is some convention, which we'll get into. Typically speaking, when you're using I generally means an index, a summation, or just an index. And then A could be any arbitrary constant, right? And then K is actually the same thing. So what this is basically saying is that I'm going to take a summation where I have the index from N, which is generally a natural number. When you use N, you're pretty much saying that you're using a natural number, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, unless you're old school like me, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I go by Pino's axioms. Pino has 0 as a natural number. How do you guys, this is an old, by the way, argument for math, whether 0 is a natural number or not. So
yeah, I think it's purely a matter of convention. I like saying that it is a natural number just for convenience, because then Z plus, the positive integers, is a convenient way to denote everything except 0. So I think it's just the convention.
I agree with you. The only reason why it's even important on summations is that in some summations, if you start with 0, it won't make a bit of difference. But if you start with 1, it makes a huge difference. So it's important to know if you're using natural numbers in a set of 1 and higher, or if you're using the set of 0 and higher, which I think I put it as Z plus, which is your non-negative integers.
Right, and let in include 0. That's the convention I prefer.
Yeah. Landon, you okay with that so far?
That's fine.
Okay. So excuse me. So again, don't get focused so much on what letters you can use here. You'll say a bunch of different types of letters, and there is a slight convention with it sometimes. X can be any variable, K can be any variable. C, however, is a constant. That is one thing that is not used as a variable. If you see C, it's a constant. And so we're going to kind of jump into how to use this particular formula. So example,
I should mention, by the way, what you're talking about, the difference between convention and style.
Yeah, this is true.
Typically, the style is that you would find lowercase I as an index, but that's just a common style. On the other hand, I could also be a square root of -1, which is a constant.
Yeah, and I'm glad you pointed that out, because way back when, before I even knew math when I was a kid, you see something like this, it's like, why are they using imaginary numbers kind of thing? I knew a little bit, but you still get confused. I is not an imaginary number here. Remember, there's only so many letters to go around, so they have to take multiple things that they can do. I is not imaginary here. I means index. It could be, think of it as any variable, X or N, if it's natural numbers. And so this could be N very easily, because 1 to 3 is natural numbers. Those are in the set of natural numbers. So how do you actually work this? Well, it's not as complicated as people think starting off. It does get complicated, but a basic summation is not that hard. And again, Landon and I have done these when we work with showing people why 0.9 repeating is equal to 1. And Jonathan loves that particular thing, right, Jonathan?
Yeah, it gets pretty amusing.
I'm sure you've had students arguing you to their death.
No, that's never come up yet.
Okay, because you got smart kids. Okay. So let's take a summation. So here, this is saying I want to do a summation of X with the index of 1 to 3. So if X equals 3, all I'm just saying is I want 3 plus 3 plus 3 equals 9. So this is just saying I want to add 3 from the indexes of 1 to 3. So basically 3 plus 3 plus 3 equals 9. If this was 1 to 2, it would be 3 plus 3 equals 6. If this would be 1 to 1, which you generally won't see a lower and upper bound like that, but because you're not doing a summation at that point, but that would be 3. So this is just telling you how many times you want to add this. That's it. This is a very shorthand notation to do that.
By the way, a quibble I would recommend is I would take out the subscript of I
on here
X, and just the summation of X.
I was there's some reasons X, why I put it in.
And in fact, I would also, just to be sure, I would say X equals 3, comma, the sum of I from 1 to 3 of X is.
See, I've seen it written different ways with the index there or not. Now I can kick this out on the fly like this.
Because the problem is that you haven't defined what X of I is. So, and I would also say X equals 3, comma, summation, right?
X equals 3, comma, summation.
You're ordering, right? You're going to read it from.
Yeah, I got you, because you want to define it first.
Yes.
Right. Yeah. Yeah.
Yeah. See, this is the little pendant stuff that I think is kind of cool, actually. Oops, crap.
Yeah. I think if we wanted to keep the I, we should say xi equals 3 for all I, or
Yeah,
something like
but
that.
that gets to be harder for people to
That yeah.
say.
That's just yeah. There's no
Yeah,
reason to really do that.
I'm not going to get into the like existential quantifiers and stuff. But how's that?
Yes, excellent.
Okay, so I'm just going to remove this little thing here. See, I love being able to do this on the fly. Isn't it great? So x equals 3. Now you've given the variable something. You give it. So now I can say x equals 3, and then do the summation of 3 plus 3 plus 3 plus 3. Now, again, use that little subscript. I've seen it done both ways. So again, I don't know if that's a style or convention thing.
The only issue is that if you do that, you'd have to say, x of 0, x of 1 is 3, x of 2 is 3, x of
You have to
3
each
is
what
3,
you have to
and
do
then,
what's explicitly.
yeah, or you have to define what the set is, right?
That makes
if
sense.
you're talking about x of something or other being a set, you have to define it. And this is much simpler. X
Yeah,
is 3, and you sum it 3 times, you get 9.
and also using this method, because if you use the index, the little subscript, it doesn't work well in Wolfram Alpha. So if you want to go check this in Wolfram Alpha, all this should be able to, you can go right, just plug it in, chug it, and just write sum 1 to 3, I equals 1 to 3, 3, and it should give you an answer.
And notice the order of precedence there. When he's talking about, he does the sum of 3, and you say equals, it's that whole thing, right? It's the whole bit is equal to. It's not 3 equals 3. He's saying the sum of I from 1 to 3 of 3 is equal.
Yeah, this part of the equation is literally equal to this, is literally equal to this. These are all 3 ways of representing the same things.
Yep.
That's the easiest way to look at it, is that if I want to represent 9, I could do it with this symbology, I can do it with this symbology, I can do it with this symbology. They all mean exactly the same thing.
Yep.
And again, people get hung up on that. They don't recognize that there are multiple different ways to express a single number.
That's exactly the issue with 0.9 repeating.
Exactly the issue.
Yeah.
Let's go to the next one. So in this, I've got to add n equals 3 here. So let me.
No, you don't say n equals 3.
Oh, that's
Right.
right.
You're correct.
You're right.
You're good right here.
All right. Okay. So in this particular case here, I just have natural numbers between 1 and 3, and it's saying take the first number here in this index 1, added to the second number of the index 2, added to the third number of the index. So when you add 1 plus 2 plus 3, what do you get in expanded notation?
Yeah.
6.
If I were your editor, I would take out the second. That sum sign should be deleted because
this one right here. Yeah, that's you know what I just recognize it. So I should get rid of that, right? Yeah. Or I could leave it. I could leave it in if I put the notation in. If I put the index, leave the index.
But I think that's clear.
Okay, I agree. So all this is saying is, if you see something like this, is take this index, put it in for n, increase the index by 1. So because again, you're working with the natural numbers 1, 2, 3, 4, 5. So the next number in that would be 2. So the next number after that would be 3. So that's all you're doing. You're just saying, I want to add all the numbers between 1 and 3, inclusive. So 1 plus 2 plus 3. Really? So that's, I mean, again, basic summations are not that complicated. And yet when I first learned these, I was like, I don't get this at all. But then looking back, it's like, oh yeah, it's pretty easy. So I wanted to focus again on other ways to write a sequence, because people get hung up on terminology. They get hung up on symbolism. They get hung up on variables and constants and symbols. But these right here are different ways of writing. Now, these are different. These are actually what's called a infinite summation or sequence. Excuse me. I'm not going to get into infinite sequences in this particular video. I think to do at the very end, only because it's something we brought up in the non sequitur show. But everything we've doing so far is finite, meaning that the summation will terminate. You have an actual number to work with. It doesn't go on to infinity. These are summations that do go on to infinity, but these are all different ways of writing the exact same thing. These are just basically an explicit way of writing the sequence. Here's a summation that inferred that the index is from 1 to infinity. It's just not shown, but that's if you see something just like this is typically inferred, or K typically infers 1 to infinity. Here's a sequence in what's called inline notation. So if I have a sub n, it's just n equals 1 to infinity inline, because you'll see a lot of times instead of being on the top and bottom, it'll just be in the same line of the sentence. This is how you write it inline notation, and then you can actually write it function Y's as well. These all mean the same thing. Would you guys agree?
So I have a problem with a few
Of course
these,
you do. Go ahead.
actually. So very minor, but the top one I've never seen that written. I think we should have plus signs between each term.
I've seen it written both ways. Now,
Okay.
the where I got this from didn't have the plus sign, but I wanted to add the plus sign.
Then it may have been just a sequence instead
Yeah.
of a series.
If you're talking about other ways to describe it, I think the more common thing we say is a sub 1 plus a sub 2 plus a sub 3 plus dot dot dot.
Yes, yeah.
And 3 dots.
Oops. Why is
It has to be 3 dots.
Yeah, I'm
It has to be 3 dots.
There we go. Yeah, I got that. Yeah. Yeah, and what that's basically saying is that it's going on infinitely. So a sub 1, a sub 2, a sub 3, a sub 4, all the way to infinity. And so that a sub n is actually literally the summation of all the natural numbers.
And by the way, there's styles of stuff too, because you're also going to deal with sets where the first element of the set is a sub 0. So there's a generator stuff. So
yeah,
so you have to be careful about in doing a naked sum on there. But it's assumed when you're in some text and some context that you know what the context is.
Yeah, like I said, it's some summations starting at 0 won't make a bit of difference because it'll just drop out, but in other ones that make a huge difference. And I'm actually, believe it or not, later on, I wanted to show people how to do an index shift. Not that they're ever going to have to use it, because again, this is just showing people if they see something in mathematics like this, what's going on with it, right? Just giving a basic overview, so they go, "Oh, okay, I get what that symbol means now," and it doesn't look as intimidating as it does to most non-math people that go, "Oh my God, that symbol, that's confusing. It's all Greek to me, literally." Right?
But we use Greek symbols because they look different than the Algebraic symbols. Of course, if you actually are Greek and you're writing in Greek, it doesn't help you.
Yeah,
Greek letters don't help you give you more symbols.
The Greek people are going, "What do you guys do to us or our language?" Yeah.
Yes.
So you might actually see it written like this. This is another example. Here you have the summation of I with the index of I to 1 to 6. And if the live chat wants to play along, how would you go about doing this without cheating? Because I've already showed you the answer. Right. You basically would say, I want to take all of the summation between 1 and 6 with going by natural numbers, which is equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6. Hopefully I got it right with 21. I double checked this stuff. So, so this is how you would write it, expanded out: 1 plus 2 plus 3 plus 4 plus 5 plus 6. So that symbol here, this whole thing is one. To me, I take it as one thing. It's just one way to represent 21. And then the next example would be a little bit different.
I like to make use of white space here, and to help people see that. So I would put more white space around the before and after the two equal signs. So it's pretty clear to say this thing is the same as this thing, which is the same as this thing. Yeah.
Also,
I can do that.
There is a difference between saying sum of I from I equals 1 to 6 and a sub I. A sub I is just being used as an index, and a sub 1 may be 42. Yes. And a sub 2 may be 97. Right?
Yeah. See, this example I got somewhere. It started with it did say I, but it was actually saying that using just I with the index implicitly means a sub I, starting with a sub I equals 1. So it was.
But you haven't defined what a sub
right.
Is, right.
Right.
And they may have defined it somewhere prior, but so you're right. You're right. That's a minor technical detail.
Yeah, here a sub I is I.
Yeah, so you'd have to say. You'd have to say somewhere in there. I would put a line ahead of time.
Yeah.
I equals I, and then.
So I could either do it the two ways. I could either take that out.
Yeah.
Put an I there. Put I there.
Yeah.
Now it's
okay. See, this is why I brought in the experts, and they're right, by the way, and I know they're right. But there's different ways. Again, if I wanted to define it prior to this, I could have done that as well.
Right.
Yep.
So, all right. So here's a little different way of looking at it when you have a variable. When you're not using the index, right here, it's actually telling you the index is 1 plus 2 plus 3. But here, I have an actual variable. I have X. It could be And so this is like you put it out. It's a dummy variable, and I just saying I want to add X 1 to 5 times, right? So I'm
So
not putting
you need an x before that equal sign if you're going to keep the summation there.
x before the equal sign. Where?
Right where your cursor is.
Right. Yeah. Right.
What do I need to put there?
So you don't have an argument in your summation. You just have a sigma, and it's equal to stuff.
Oh,
So,
I see.
Yeah.
So before the equal sign, put an x.
Yeah.
Got it. Okay.
Good.
Yeah, add a space in here. So you like white space, and I'm a fan of it too. So darn it. That tilde is actually a way of actually doing a white space.
Non-breaking. It's called non-breaking space.
Yeah, absolutely. Yeah. Did I?
Oh.
It's okay. I'll fix it.
And it's one of those style things as well that you have to
Latex.
go. If you're going to submit to a journal, you must submit to the editor's proclivities and style guides and so forth.
Yeah, and by the way, I'm using OpenOffice Math. I've also used LibreMath. They're almost identical. I happen to personally prefer OpenOffice, but it's just my preference. Either one is really good. Some people prefer LibreOffice. I run Libre on my Linux, and it's just fine. It's almost literally the exact same thing. I just, excuse me, from personal experience, find that OpenMath has less little issues. I just think
I've never tried any of those. I'll have to try them though, because it's annoying to whip out latex for something that really you don't need to use it for.
Oh yeah, no, I'm a big fan of latex, but the problem is again, it's overkill for what I do.
Exactly. Yeah. I would definitely make use out of this.
Oh yeah, use OpenOffice.
It could be TROF and EQN and TBL.
Yeah, I don't know. Not going to happen. No, try this program out. I'm telling you, OpenOffice Math is very simple to learn. Yeah. You can learn it in literally a half hour, pretty much, maybe an hour. And you can do things on the fly, just like I've done. And there's multiple ways of to do things. And so it's pretty simple. All right, so here's like I said, so here's basically what it's saying is I want you to add X 5 times rather than I'm not putting a number into X here. I'm just saying I want to do a summation of x1 plus x2 plus x3. I just want x 5 times. So my summation of x from the index of 1 to 5 is 5x. And the solution would be this. Agreed?
Yep.
Yeah.
So people can notice the difference here. Here, I'm actually putting in something into the dummy variable here because I'm using it as the index. So here I'm getting I'm not saying I 5 times. What I'm saying is each iteration, as I step from the natural numbers from the indexes from the lower bound to the higher bound 1 to 6, I'm going to equal 21. And so this is where I think back when I got confused, and I'm like, what's going on here? I don't understand. But if you look at it, there is a difference between the summations. You have to understand the concept of what it is asking you to do a summation of. Right? Be agreed? Okay. So here we're getting a little more complicated. Here, in this particular summation, we're going to start with a different value for the lower bound. Instead of having 1, we'll start with 2. And we also have a multiplication going on, right? So we have 4, which is a constant, multiplied by k. And generally from what I found, k in summations can be any kind of arbitrary thing. It's just a variable, just like any other. So here's asking you, I want to take the summation of 4k with each iteration of k starting from the lower bound of 2 going to 4. So basically, I'm going to plug and chug it explicitly. I have 4 times 2 plus 4 plus 3, 4 times 3 plus 4 times 4. If this was an index going to 5, I would add another element in there, 4 times 5. And that would be, again, going out as many times as you're having to your upper bound. If this was a infinity, if this was called a infinite summation, clearly it would be going up toward infinity, right? It wouldn't be convergent. It would be divergent. Mm-hmm. Yeah. Which again, we'll have a separate video on convergence and divergence because I do want to kind of get into that more explicitly because people have such a hard time with that 0.9 repeating.
Some physicists may think that would be like negative, 1/16 or negative
112.
112. Yeah, with the 4 though, who knows?
Oh yeah, you're right. Yeah, with the 4. Yeah, we've discussed that before. And when you have 1 plus 2 plus 3 plus 4, and you're doing that divergent series, and I've tried to explain to people this, but it's so complicated. The problem is when you do what's called an analytical continuation or a different way of doing summation. Mm-hmm. One way to do it will get you negative 112. it's based upon the Zeeman function, right? The Zeeman, is that a
Riemann.
Zeta Riemann function?
Yeah,
Riemann.
yeah,
And
that's
trying to
right.
explain that Zeta function is nearly impossible for me because I haven't done shit with it in ages. So you guys might have to come on and explain the Zeta function because the actual calculus for that is pretty difficult.
Right. So
So-
I do think it's a
but we're-
meaningful. Sorry, go ahead.
Yeah, no, go ahead, Jonathan.
I
I was just going to say
we're
it
doing
is
some
a,
very simple stuff here, right?
Yeah,
Yeah.
we're keeping it simple. Go ahead, Jonathan.
I was just going to say that negative 1/12, I do think it's a meaningful assignment to the series, but people confuse it as it being literally the sum, as in the the limit of the partial sums.
Right.
So it's a different definition, but it is a meaningful value. It's just
It's meaningful in physics. Actually, it has
Right.
actually some use in orbital mechanics. So there is a use for it, but it doesn't literally mean that summation is going to, if you add them all up, you're going to get negative 1.
Right, exactly.
You are getting you are unfortunately going to infinity. You're going to have an infinite value, which is not even a value. It's just infinity. Infinity is not a real number, people. And I mean that very literally. Infinity is not a real number.
That's not a pun.
It's not a pun. So I know this is going to be a little more technical, and the only reason I included this because people that do get into math may need to understand a little bit about this. And you'll see this type of a notation a lot, and you see especially the expanded version of this when you get into college algebra, even when you start dealing things like Pascal's triangle, binomial expansions. You see this expanded notation often, and it is very confusing, but it's not really. But what this is actually saying, and hopefully you guys can jump in here because this is way out of my element when I start dealing with mapping. But the definition of a summation is literally a set of natural numbers that maps to the reals. So it's a function of natural to the reals.
So that would be a sequence. A sequence.
God damn it, you're right. Your sequence.
Precisely what a sequence is.
That's the definition of a sequence. You're right, and I know that, and I don't know why I write summation.
That's fine.
This is why I have the experts.
Because I was trying to figure out what in the world are you saying. Okay, yes, definition of a sequence.
Let me change this. Now I got to find this in here. Go ahead and talk about this expanded notation too, real quick.
I mean, I know you're talking about the mapping of N to R, but I think in this particular case, it's not. Well, yes, it depends on what. It depends actually on what a sub I is.
Well, normally it's either a set of the naturals or a subset of the naturals, either or. As for a function.
But I guess I don't understand. I don't understand why the line of the mapping is even there. Right? I think that first line confuses people because one, you're introducing notation, they haven't been mapped.
Mm-hmm.
Two, you haven't defined what R is or the mapping stuff.
Well, R is
a
real
definition of sequence, and you get rid of that first line. You just have the summation.
Well, because people might actually see it written like this sometimes. The N is your natural number set, R is your real number set, right?
Sure, but I think that maybe we should define sequence first, because a sum, you can view it as, if it's an infinite sum, it is the sum of the values in a sequence.
Sure.
So we could make these two things more relevant to one another if instead of a sub I, we used f of I. Then we're saying, let's sum the elements of this sequence.
Ah, okay.
Yes,
So,
yes.
all right. Gotcha. So if I change this to a function.
Yeah. F
now
of
I'm going to
I.
be, okay. Now.
How does that make more sense?
So
yes.
plug in I as normal function notation, not f sub I, but f of I.
Yeah, I got you.
Yeah, that would be
perfect.
As
a function.
Okay.
Yeah, I think that's the intent here.
Okay. This is, again, experts.
And that would need to be changed throughout, though.
Yeah.
So a sub m would be f of m, and a sub m plus 1 would be, and so on.
And it would be parentheses, right?
This would be a subscript, then. It would be
right,
that.
No subscripts.
No subscripts.
Yeah.
There you go.
See, this is one of those things where you understand the concepts, you go, okay, I know what the hell they're talking about, right? This is why I think concepts are more important.
Of course, you have to have the parentheses around. You forgot your.
Hang on. I'll fix this. You got to change the M here too. How's this?
Yay.
That work?
Okay.
Yes.
So again, this is why I think it's critical to understand the concepts, because if people don't understand those concepts, what you're talking about, I wouldn't be able to fix it on the fly.
So we could say that this is the definition of a sequence, a map from the naturals to R, and then this second line is the summation over that sequence from N to M.
Right.
Yep.
M to M. Sorry.
So this is literally how a definition would work in mathematics. It is it's defined. The sequence is defined to be this, right? So it isn't any kind of arbitrary thing. It is saying this is what it means to be a sequence from the lower bound of M to N, and then it shows it explicitly. Okay.
Yeah.
So, excuse me. I kind of wanted to get into, and I know this is going to be a very short presentation. There's not a lot for the basics of summations. It can get, like I said, get really complicated quickly when you're dealing with double summations and summations of summations and weird other stuff, but I'm not going to get into any of that. But I did want to show working with different indexes, because this has come up before when I was dealing with 0.9 repeating. People didn't understand shifting indexes, and honestly, it's not that hard, but at the same time, if you've never done it before, it's not intuitive. I don't think. I don't know. But let's see if I can explain this, and then hopefully you can jump in, and because I really made this up as I went along. So this, I have the index 4 to 5 of the summation of x. And I wanted to show this conceptually, that it's literally just asking, again, this is concept, that it's literally just saying, I just want the fourth and fifth term actually this would be the summation. Sorry. These are the summation.
And are we talking about x here, x sub I?
X with a sum of the index of 4 to 5.
Is it x sub I? Because I'm seeing down below, given that x sub 1, x sub 2, blah, 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 blah.
And then it's 5x. So it.
Oh, I see. Shoot. Okay.
So we want to remove, it looks like, all of these indices.
Yeah. So let me
subscripts, sorry.
Okay.
Let me get rid of these. Shit, got rid of too many X's.
It has the added value of making it simpler.
Yeah. Okay. That. I'll do on the next one too. Is that better?
Yeah.
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 Okay, I got you. Makes sense. Okay, so basically, it's just saying I want, if I have that, if I have 5 x's, right? Because I'm on x 5 times here. What is the fourth and fifth term? Right, I'm just adding those together. So I'm just getting 2x, right? If this was 1 to 4, should be, let's see, 1 to 4 would be 4x. If it'd be 1 to 3, it'd be 3x. And you'll find that the top, there's actually a rule here. If the bottom bound is 1 and the upper is whatever number is, then that's how many times you do it as a constant. And I'll show that rule here coming up here. But this is conceptually saying, I want the fourth and fifth term given if the sequence was from 1 to 5. I'm just adding 4 and 5. And again, this is a concept thing, right? This isn't actually how you would do it, but would you say conceptually this works?
Sure.
Okay.
Yep.
So given that, and given some of the basic rules of summations, if you ever have to do these things in real life, there's a couple handy rules that are critical to know. The first one is this one. This is saying that any constant, let's see here. Any constant, if you take a summation of any constant, it's equal to the multiplication of the top bound by that constant. So going back to 1 to 5 here, let me see. Someone's going to message me a million times here. Okay. Okay. So this would be, again, going back to here, right? 1 to 5. All I have to do is take 5 times x, right? So the top bound by times this constant equals 5x, right? So this is literally an actual basic rule. If this is a constant, you can take the top bound and multiply that by this, and you'll have the answer to that summation if the lower bound is 1. This always works if the lower bound is 1.
So this rule is the distributive property. So it might, I would mention that, or link it to the term, because it is literally the distributive property.
This is based upon distribution, and the next one I'm going to get into is the associative property. But yeah, this is because of distribution. Do you want me to write that in there?
I probably would. I would say I would call this the distributive property.
Okay.
It's.
Let's see here. Now I got to find. find this in my little thing here. Added basic rules. Where is
Or
that?
maybe a note in parentheses,
Yeah,
however
put
you want to handle it.
a parenthetical note would be better.
The only thing I don't like about this
Example, or
program is very
say
hard to
note,
find
example
things.
of distributed property. Or something.
Yeah, I think that would be a good way to handle it.
Example of
No,
distributed
this is
property.
an example of the distributed property. If you're trying to make
Right.
distributed property example.
I can actually make it. I like the italics. That's fine. So does that work? That way it
Sure.
stands out a little more.
Yep.
And yeah, that is based upon the distributed property. Okay, so here would be an example of that. If I have the index starting with lower bound of 1, going to 10, and I have any constant here, simple. All I do is just take the top number, times it by the constant, you're done. Can't get much easier than that. This is about as basic a summation as you can ever hope to get, I think, because you already know how to do a multiplication. So if the C is 1, it's 10. If it's 2, it's 20. If it's 3, it's 30. And if you actually did it explicitly, it would make sense, right? Why is that the case? So this is just a shorthand basic rule of constants. Here's a little more explicit example of constants being able to be drawn out. This is based upon association property.
Well, this is literally the distributed property.
Oh, this is distributed property too, right?
The previous one is an example.
This is uses
an isolated case of the distributed property, and I think the second one is literally the distributed property. I would say.
Yeah, so this would be a very explicit use of the distributed property. So what this is basically saying, if I have any constant times what your summations is, I can draw the constant out for across. I call it across the summation. Is that good terminology?
That's fine.
Okay, so I draw it across the summation. I bring it out to here, and there's many advantageous reasons to do that. One, it makes things so much simpler when you're doing the summation, because now I'm just left with something you're used to. This part here, I can just do the summation, and then times it by a constant. That's it. Boom, done. So I don't have to take this constant and multiply by every single iteration. I just draw the constant out, and let me give you an example of this. So let's assume C. Go ahead, Len.
On the C equals 5, if you say comma and a sub k equals k.
Right. So that seems to be a recurring.
Yeah.
In that particular section, of course, we fixed it before, but and a sub k equals k.
Had a comma there.
Excellent.
Yeah. Like I said, these are the little like nuances that math people pick up.
Right. So we would use a sub k generally when we don't want it to just be the index values. If we want it to be the sum of some sequence, some function. So the definition as the sequence from a map from the naturals to the reals is precisely the naturals are the index values, and they're mapping to a sub k, which may be a real number. So that's the idea. The sequence mapping definition is captured by the notion of having that subscript. That's the input, and a sub I is your output of the function.
That's a great way to put it. And I think that actually will be seen here explicitly that way, because when I draw the constant across the summation, and I'm just literally working with this part, then what do I get? I end up, actually, you know what? I need to draw this. I need to put the C over here. Dang it. So let me fix this real quick, because this is my whole point of showing this. So I got to add C here. Is that right? Yep. I got it. Okay. So here I'm just I'm just literally saying, what's the summation of 1 to 3, which is 1 plus 2 plus 3, and I'm timesing it by this constant 5. That's it. So this right here, this part of the summation is just this right here times a constant. And so 5 times 6 equals 30. Another way of doing it is just taking 5 here, right? If I'm explicitly showing the value of C, then I'm just saying 5 times this part, right? And this part is equal to 1 plus 2 plus 3. 5 times 6 equals 30. So these are all equivalent statements. Or, they're equivalent, what would be a good word? Nomenclature?
Sure.
Yeah. So
expressions.
Well, if I take this part here without the equal, then yeah, that expression here, then that would be equivalent to these things. There's just different ways of representing the same thing. So this is why I think critical it's critical people understand the concepts rather than get fixated on, well, what letters you're using.
Definitely. Yeah, definitely.
Because again, a lot of times when you see these things written out in papers and things of that nature, the author can pick whatever reasons they want to pick certain things, right? They may use K, they may use J, they may use I. There's different reasons why they have a preference for whatever they're using. And so you may don't get hung up on this being, why is this K equals 1 to 3, why is N equals 1 to 3, right?
You're absolutely right. Like, in fact, just this past semester when I was giving a test on systems of equations, if it was a system of 3 unknowns, I would use X, Y, and Z. But when I got to 4 unknowns, I used X sub 1, X sub 2, X sub 3, and X sub 4. And I did that without thinking, but they had no idea what I meant by that. They'd never seen subscript something before. And really, those are just 4 different
completely variables. Right.
Yeah, exactly. So that is a very important thing that has to be like really brought up and really dwelled upon for a while. Just getting over the
symbol confused by that. Yeah, definitely.
Yeah, they said I was trying to trick them. I'm trying to trick.
Wow.
A professor trying to teach to trick.
Professor.
Yeah. Well, you're close enough.
Oh yeah, thanks.
When you get that official title, though.
That would be awesome.
Oh yeah, it's close. You're getting close. Addition, subtraction, summation. So this is another critical rule that I think comes in very handy. You'll see it written different ways, because you can actually explicitly do this with plus or explicitly do it with this minus. I just combine it with a plus and minus symbol. I've seen it both ways. And so what this is basically saying is that, and this is where it comes into the additive, just basically
this is commutative
property, because how I add them makes no difference, right? I mean, if I add 1 plus 2 and 2 plus 1 is commutative. Right. So it doesn't really matter the order of which I'm adding something. Multiplication is the same way. It doesn't matter which order I do multiplication. So this is just basically saying, if I have 2 summations, how I add them together makes no difference. And the way we would do this as an example, let's say I have this expression here, 2k plus 5. Now, again, normally I can draw things across the summation. I will be showing how people do that later on. An example similar to this. But here, it's just saying, I want to take, and by the way, there's some distribution going on here, is there not? Isn't this distributive over the 2K over addition to the 5K in some ways? Now, I've never seen it written that way, but I had to think about this the other day. I'm like, am I not distributing this in some ways between I'm taking the summation of this, but it's not?
Okay, so I think that there is a way to view, you could view that the summation operator is distributive over addition.
See, I was conceptually thinking that the other day, but I
think it is. Yeah, I do think that it's reasonable to view that as.
No.
Yeah.
I got to point out that plus minus symbol. There's some
complications involved. That needs to get it.
Yeah. I would have written it with 2 expressions.
Oh, you would have separated this. I got
plus minus.
I know what you're saying. Yeah, I think now I did see this written exactly like this. So this I did take somewhere. I think I agree with you.
There's the implication here, but
should you write it plus and then write an additional one here with negative?
Well, no, I would give you because you're not trying to teach them about the plus minus operator.
Well, but this is the same. The way this is interpreted. If it's plus on the left-hand side or right-hand side, use plus on the left-hand side. If it's negative on the left-hand side or right-hand side, use negative on the right-hand side. That's how it was to be interpreted in the notes. But this is probably abusive notation.
Yes, it's abusive notation, and of course one could also say, well, no, over the set of A and B, plus and minus varies.
Right. The issue is, am I choosing a plus and minus to stay consistently throughout the entire summation, or is it on a turn by turn basis?
Gotcha.
Yes.
So if you really wanted to be precise, which I know you guys are, because that's why I brought you in, so you actually probably should write it this way, I think.
Yes, I think that would be clearer for somebody.
That'd be better.
Yes, I'm happy.
Yeah. See how fast I can do that in this? That's what I love this program. I'm telling you.
Yeah.
So yeah, you're right. So this probably shows somebody better how the order of which you add something and the order of which you subtract makes no difference. So here I'm just saying, okay, I'm gonna just I think you can distribute this summation sign. I'm fine with that. Just distribution over addition. So I'm taking the summation of 2k. I'm summation of 5 with the index from 1 to 3. So I separated these out just so people can see conceptually how it is. This expression here, or this part of the equation, expression doesn't have an equal sign, but I still use that terminology. Is that okay to do that? To me, I call this an expression on this side of the equation. Yes. Is that inappropriate or is that appropriate?
It's fine.
Okay.
That's appropriate.
Okay. Yeah. So this part of the equation, this expression here, when you take the summation, I'm just taking 2 times 1 plus 2 times 2 plus 2 times 3. And yes, I could draw this 2 out here, like using this rule, the distributive property example. But I haven't for this particular case, but I could. But this expression here sums to 12. This expression here is basically just 5 times this number up here, because again, my bottom limit is 1, so I can use that other rule. 5 times 3 is 15. Add them together, what do you get? 27. So this whole expression here is the same way of saying 27. And I have checked that on Wolfram Alpha. So does that make sense to the live chat? I'm sorry, I have not been asking the live chat enough if they've been not too lost on this. They seem to be doing okay.
They have the same value.
They have the same value, obviously. Right? They represent the same value on the way I say it as they represent the same numerical value on the real number line. Just a different way of expressing it. Yeah. Okay. Another one is very handy, and there are multiple different ones of these dealing with like k squared and k cubed. I'm not going to get into those. So I just want to give the very simplest one, which is a summation formula. When you have the index from 1 to n, if you want to add up all those numbers, there's a very simple way of doing it. And there's an old story, a math story, and maybe you guys can validate this. I think I can't. Who was it?
It's Gauss.
Gauss. Okay, so Gauss was sitting in class one day, basically, and the teacher had asked the students. I guess
as a student, Gauss was a student.
He was a student.
He was learning,
and I guess the teacher just wanted to pass time or something, I guess, and just asked him to do this big old long summation, and he figured it out pretty much instantaneously by doing this in his head using this shortcut. Right? Is that so? That's a true story.
Yeah, I've heard the same. So I'm not sure. I can't say for sure, but I've heard it, and it's reasonable.
It's definitely plausible. Sure.
Yeah.
So what he did was he just basically took the upper bound and times it by the upper bound minus 1, and you can see why this works. By the way, I wrote this in 2 different ways only because, excuse me, again, I want people to understand concepts, and people have not had algebra don't seem to realize that this right here is the same thing as this. Just because it's not over the horizontal bar, it doesn't matter. Multiplication, it's commutative. So it doesn't matter. I have n times this on the top or just n times this. Same thing. Don't get hung up with that because they mean exactly the same thing. So in this example, from k equals 1 to 4, where I have 5k, all I'm doing is I'm taking the upper number and I'm timesing it by the upper number plus 1. I'm sorry, not minus 1, plus 1. So is it? Yeah, it's plus 1, right?
Plus 1.
Yeah, yeah. So what's 4 times 4 plus 1 is 4 times, let's see, 5.
4 times 5.
4 times 5 times 5, which is 5 times 10 equals 50. There you go. So because I got the dividing 2 here. So by the way, like I said, this 5 could be up here too. So it'd be 5 times 4 times 5. All right. So I have 20 minus 5 times 4 is 20. 20 times 5 is 100. 100 divided by 2 is 50. So any way you do this, you're going to come up with the same numbers. So this is a very shortcut way of doing it. If you are actually starting with 1 as your bottom limit, going to n, you'll see this one often actually. And another one whether you'll see often is when you have k squared, but we're not going to get into that particular one.
This is also a good bar trick. You can challenge people to add.
And I know we do have a stream tonight on sequitur. We're doing something with flat Earth, so in about 25 minutes.
Oh dear.
Oh dear. Okay, so let's do a practice problem, and maybe the outside chat can kind of work along with us. So
okay,
if I wanted to
get your pencils and papers ready.
Get your pencil and paper. Yeah.
Assume the position.
Downward doggy. That's how it is in math. All right, so practice problems. When you don't have an equal sign, you evaluate an expression. So in this particular case, you evaluate this expression. You're not solving. you're evaluating. You solve equations, you evaluate expressions. Just one of those little things that's good to know. So the answer is potato. Yes, red eye. This is good. Red eye is so smart. I love red eye.
Well,
Always
actually,
potato.
red eye is correct. The answer is potato for certain values of k.
If k is equal to if k is equal to turnip. So so let's evaluate this. The best way to do this is basically using the rules that we showed above. So the first thing I would do is I would show that these are two separable expressions by distribution of the summation sign over addition. And so I'm just saying the summation of 5k plus the summation of 8. That's it, right? So very simple way of starting off. The next thing I would apply would be the rule of the constant here. And so I'm going to draw the constant across the summation and bring it over to this side. Okay. So again, these are just manipulations of this expression to make it easier to solve. That's it. So then I would actually just do the summation. So this right here is equal to this, what we did up here, right? I'm saying, excuse me, a very shorthand way of doing it is just taking the upper bound, times it by the upper bound plus 1. That's going to actually give me 45. And here you just have a constant, right? So, and here the constant is equal to constant times the upper bound, which is the
so you're missing a plus sign.
Where did I miss a plus sign?
Keep going right there. So we have 5 times 45 plus.
Plus.
Yeah.
Okay.
Yeah.
So I'm just evaluating these two expressions individually here. Boom. I got 5 times 45. I got 9 times 8. And then if you add these all together and you times 5 times 45, you're going to get 297. Again, I've already checked through.
Now, by the way, for the case that Red Eye brought up, this is a legal summation as long as it's in Western Australia, as long as it's less than 50 kilograms.
There's a pun in there somewhere.
Well, there's a law in Western Australia that doesn't allow you to accumulate more than 50 kilograms of potatoes. So
really?
Less than 50 kilograms.
You know what?
It's a legal expression.
I think I understand that law because people can actually die from potato fumes. If you actually have potatoes in a basement and you let them sit there for too long,
ferment,
yes, people have died. Whole family died. The father went down there, the daughter went down, and a whole bunch of people went down to the basement. They all died from potato fumes. They are lethal.
Wow.
Yeah.
I mean, given the number of the things that are lethal in Australia,
Lisa,
50 kilograms is probably lower on the list.
But I got to tell you, if Red Eye is going to go, that's the way to go. Death by potato fumes. He would be appreciative of that way to go.
Awesome obituary.
Right, exactly. So, okay, so some important takeaways. We're getting toward the end, sort of. Again, don't get hung up on the symbols. These three things, even though they look completely different, mean the exact same thing. Again, this is where it's critical to understand that I is not an imaginary number here, right? And I think this is why personally I wouldn't use I for the index. Here you know that I is being used for the index, but if you don't understand the concepts of math, can you guys see that how easy it would be to think, okay, that's an imaginary number squared, right?
But it depends upon your context, right? If you're dealing with a particular types of number theory, that's fine, right?
Agreed, and there are complex
and
things.
if your electrical stuff, it would be J that you'd want to avoid, and so so it's kind of depends upon the conventions.
Damn those electrical guys with J.
Yes.
Yeah. But yeah, you're right. Yeah, and so it does depend on what framework I guess you're working in. The point being is, don't get hung up so much on symbology. Understand the concepts, because you're knowing now that this is not I squared, whether I see K there or N there. But personally, I prefer N here. And the reason I prefer N here is only because I like the concept of dealing with natural numbers. And N123 is to me showing that these are natural numbers. Now, again, maybe that's personal preference. But Jonathan,
I guess it depends on what your context is.
Well, again, K is arbitrary. If I want to kind of highlight that I'm using arbitrary things, then I use K. K is meant to be generally arbitrary. So I guess it depends on your purpose. But for most things, I'm going to use N when I do my limits, except when I'm using, like for the definition of a sequence using actual calculus, it actually uses limit of using for K. But again,
But we're dealing with the difference between
because
style.
K is generally
No,
1 to infinity, so
again, it's part of the style, right?
it's
So,
part of the
so if
style.
you're dealing with papers in astronomy, you're going to see something different than you're dealing with something on elementary number theory.
Right, but if I'm reading something and I see K off in my head, I think K is going to be 1 to infinity because that's generally what it's used for when you're
So
doing.
context comes up a lot. Like
Yeah.
sometimes like if we're talking about say something with 3 coordinates or whatever, and we just use a summation symbol and we don't put any index, it's kind of understood that we're summing over 3. We're summing over 1, 2, and 3. Like if we're talking about 3-dimensional vectors and we write sum of a sub n, by context, we just know that's a1 plus a2 plus a3, and that's it.
Yep.
Right.
So
Yep.
context comes up a lot here.
I definitely agree. Here's a good rule of thumb. N is typically used for natural numbers as sequences are in the set or subset of natural numbers where a sub n is an element of natural numbers. Again, this is just fancy symbology. All this is basically saying is that n is going to be, as a subscript, which is here, is going to be equal to some natural number. That's it.
Is there a comma missing there, right? Where your cursor is? Are you
Here?
saying a sub n times n?
And a sub
Or are
n.
you saying, or is there, do you need
No,
a
I'm
comma?
saying that the a sub n is this should be a comma here.
Okay.
There you go. Where n a sub n, where n equals an element of n.
Okay. Thanks.
Okay. K is actually as a sub k is most often understood to be an arbitrary number between 1 and infinity. So if I have a sub k, this is inline notation.
Now, I will say that oftentimes, again, in number theory, you'll see a sub I as a style, and you'll see P reserved for primes and N for composites and primes.
So it really kind of makes a difference on what you're going for, I guess, right?
Yeah, context is important.
Yeah.
I mean, you can use variables A, B, and C, but if you're dealing with physics and cosmology, and you start defining C as a variable, you're going to confuse your formulas.
Exactly right. And that's going to be why this is probably why you don't use certain letters in certain contexts, right?
I would say that in the case of subscripts and indexes, nearly any symbol you use is going to refer to a natural number. Like I wouldn't think that if anyone used a sub k, I would never think that they were talking about a sub root 2 or a sub 1/2.
Right.
I would think it's always a natural number.
I agree. I agree with Jonathan.
Yep.
I think the common indice variables that people often use are I, J, and K, or X, Y, and Z, or A, B, and C, or.
Okay. I have to do something real quick. I'm going to leave this for you guys to explain index shifting. I'm going to put it on the screen for you, and then maybe you guys can explain how to do index shift. And basically, all I did was I just redefined. And now there are different ways if you can do this. You don't have to actually change the actual index or shortcuts to this. I know, but I wanted to show the concept. So the way I did this was I actually changed the index from one index k to a different variable I. Again, you don't have to do it that way, and then by shifting the index, you have to shift it from the opposite sign on the what you're doing the summation of. So hopefully you guys can figure this out. Give me like 2 minutes if you can.
Sure.
All right. So maybe Jonathan, maybe you want to try to maybe explain this, or is this confusing to the way I did this?
No, it looks fine to me. Yeah, so I would say the best way to explain this is that if we want to shift our index here, so I don't have the cursor, unfortunately, but we basically have to compensate for that shift in index. So I kind of, I don't want to introduce something that's not here, but if we have a function and we shift the input value, like by adding a constant, we shift the graph horizontally. It's kind of the same concept. So we want to compensate for that index shift by shifting the input. By changing the name to a different index, we compensate for that by kind of undoing the shift within the expression itself. That's how I would explain this.
Yeah. So you see what Steve has written here. The first summation expression with k is over 2 to 4. And that's the same as I plus 1 going from 1 to 3. where k is I plus 1. You're just think of it, you're just doing as a substitution. But notice again, when you have your first summation, where it says sum k from 2 to 4 of 5k, if you're going to and we said k is I plus 1, you just can't turn around and change k to I plus 1 because the index is k. You have to also change the index as well. Because think about that second summation, right? If you look at that second summation, if we said I equals 1 to 3, if that was k equals 1 to 3, that'd be a very different expression.
Okay. Yeah, let me kind of, if I can, let me show why these things actually work, why an index shift actually works, because I broke it down, and again, I pulled this out of my ass. I made this up. So, so if I have this summation here of k equals 2 to 4, 5k, and I wanted to shift it to something else, and I wanted to shift it from I to 1 to 3, all I'm doing is basically make this part right here is equal to this part right here. They're the same exact thing. I'm just taking the different elements from a different point, right? I'm just saying, excuse me, I'm just taking 5 times 2 here. It would be 5 times the lower index, so I have 10. But here I'm just taking it from 1, but I'm actually on this side of the equation, I'm adding it 1 plus 1. So 1 plus 1 equals 2 times 5 is the same thing as this. So 10, 10, 15, 15, 20, 20. So just by changing the where I'm starting on the index on the left-hand side here, then on the right here, then it's going to equal out. It's going to be the exact same thing. I'm just shifting it. That's the best way I can explain it in a nutshell. But I don't know how you are also explain it. But again, normally if you do this with a real world example, you're not actually going to change the index. You don't have to. You can still keep it with the same index, right? It's just I want to show conceptually if I'm doing a new index, I can do it that way.
Yeah. My point was on that the expression where you have your cursor. Mm-hmm. If you have to change the index from k to I for that to make sense. If you left it as k.
Oh, okay, I got you. So this has to be k. Does this have to be k? Let's see here. Is that right? And then I change this down to k? No, that's not right.
Because you've just messed it up.
Yeah. This be all right. Okay. So what should be changed? Because
notice that those two expressions. Steve is correct here. There's no problem. And notice what he did when he changed k to I plus 1. He also changed the.
I see. Change the index. Yeah. So if I change the index from k to I here, I got to change it on the argument as well, or the semantic. Yeah. Yeah. Again, all this is really doing is I'm just changing the index. I'm just saying, okay, what am I changing the value from? Well, here's going from k minus 1 if I want to change this to 1. So I is now equal to k minus 1 because 2 minus 1 is 1. That's it. And then if I want to figure out for k, I have to say, well, k equals I plus 1. So that's what I'm going to add on this side because this is what k is going to be equal to. So this equation here, all I'm doing is I'm taking this minus 1, I'm moving it to the right hand or left hand side. That's it.
Exactly.
I'm just solving for k. And this is where shifting gets confusing. And this is why I like to do it step by step. Okay, what am I trying to do? Well, I want to shift k to 1. Okay, I want to create a new index. I want to subtract 1 from k because I'm 2 minus 1 will give me 1. And then I want to solve for k because I want to change this. I got to change it on this side as well. So k, move the minus side, negative 1 over here. I have you obviously I'm going to cross the equal sign. So what do you do when you do that? It goes to plus. So k equals I plus 1. And that's why I get this value here. That's it. This is how you do an index shift. And again, you're probably never going to have to do it. But I just want to show somebody that. And we are going to leave off with this only because this was brought up on the non sequitur show the other day, which we are going live here in probably 15 minutes. So I got to wrap it up. But Zeno's paradox, some flat earther said was not resolved. Well, guess what? It really is. And this is the reason why it is. I'm not going to go too much in detail on it, but going back to inline notation for a function, what this is basically saying is that if I have the function of 1 over 2n, and I take a summation of that to infinity. This is one of those times where I'm doing an infinite summation. Basically am ending up with 1/2 plus 1/4 plus 1/8 plus 1/16, et cetera, all the way to infinity. I'm not going to get into this video. I'm going to do another video on this, I think. But when we just start getting into partial sums, I think, Jonathan, you had mentioned them earlier.
Mhm.
Partial sums are critical to understand how summations work. So I'm not going to get to the derivation of how we got to this partial sum formula. But I just wanted to show people using math, you can actually demonstrate Zeno paradox is resolved. And so I did this. And this is basically saying, using a partial sum formula, that as you increase from n equals 1 to infinity, this is what the dots mean, you end up with a summation of 1/2 plus 1/2, plus 1/8 plus 1/16, etc. You take the limit of that. The limit of a sequence is equal to the summation of that sequence. So and again, going back to other videos we've had where we've done limits, so this is why I'm not talking about it too much. If you want to go learn limits, I have 2 other videos on limits. But the limits here, basically, as n is approaching infinity here, what's going to happen? This is going to go to 0, right? So what is 1 minus 0? 1. The series converges to 1. Therefore, the limit of that sequence is equal to 1. This is why when we say, when you take that summation of 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, what does that give you? It gives you 1.
Yeah.
And
By the way, I will point, it's important, that Steve talked about this Zeno's paradox. Paradox does not mean unsolvable problem. Paradox means it seems to be absurd,
right,
or self-contradictory statement, or it's a proposition that's seemingly absurd.
All right. We should really call them
it. Investigate it.
Paradox. Well, there are the
veridical, well-founded, or may or may not be proved well-founded or true.
There are veridical paradoxes that aren't even paradoxes. They're just apparent paradoxes, right? So a veridical paradox would be a paradox that's not even close to being an actual paradox. But yeah, paradox doesn't mean it has to be unresolvable. Like, for example, I don't think that EPR is a paradox, right? The Einstein's Pulaski, that's not a true paradox in my opinion. And you're the astrophysicist, dude. But would you agree, Landon, that that's resolvable? And we are going to have a separate hanging on local realism.
Well, but it's also on the beholder. Again, paradox seems it's a statement or proposition that seems to be either absurd or contradictory. But
at face value,
investigate it. It may prove to be actually a well-founded process or principle.
Yep, I absolutely agree. By the way, Jonathan, if you want to do one on quantum. People have been asking a lot about local realism and why I think local realism is bunk, and why I hold to the Copenhagen interpretation. A lot of people have asked me that. Again, honestly, the only way I can actually say is personal preference. Obviously, the multi-world hypothesis works. If you want to use Bohmian mechanics, that's fine as well. I just think it adds additional assumptions. I want to be able to explain Bell's inequality and such in a way that why I believe there's no local hidden variable model that will work in any type of modeling, simply because it doesn't satisfy Bell inequality. So if you want to join us for that, Jonathan, that'd be great.
I would have some reading to do. I'm a pure mathematician. I live in La La Land. I don't know.
Well, you can check the math. Landon's got the physics down, I think. And I will be bringing in Dr. Kroon, who's an astrophysicist. So
awesome.
We're going to have plenty of people for this kind of expertise, but the math you can definitely check. But the way I'm going to try to explain it is that with the Bell inequality, if I remember correctly, and I haven't really looked too much at it, but our expectation for if there's a local hidden variable should be about 55% of the time, but unfortunately we only get it to 50% of the time. So no model can explain it. I think it ends up to be 5 over 9 if you look at all the different possibilities and you just kind of bring them together and say, okay, what would I expect given some randomization for spin up, spin down? It actually would expect to be 5/9 of the time, which is about 55%. We would have this expectation with a local hidden variable model, but we don't see that. We actually see it to be literally half of the time. And so I don't believe there's any information in that system prior to an event like weak nuclear decay or spontaneous fission. I think it's completely random. I think there's no rhyme or reason for it. And I'm okay with that. But that's philosophy, right, Landon? That's the philosophy of science, which
Yeah. Yes. But anyway, I don't want to keep you from your You're more factual based
Dumpster
show.
fires. Yeah.
Yes, I still am amazed that some people are actually proud of being a flat earther. It is
Bizarre,
it's
isn't it?
it's like people proud of 2 + 2 = 3.
Yeah, I don't get
Which
it
does, by
either.
the way, 2 + 2 does equal 3 for certain values of 3.
Yeah, well, 1 = 0 for ring theory and the zero ring. So it all depends on what you're working with. Try to explain that to somebody.
That's a
Because
joke, by the way. I said a joke. Right?
yeah, well, yeah, but it's funny in Gawa theory, you can make weird things like that happen, right?
Uh,
I'm trying to
in
think of
term,
a ring mod something where 2 + 2 is 3, and I'm not sure that happens.
Well, but even using mod though. Um, well, again, these are all to me. I just look at them all these qualities, or even if you're using something like a mod, or even if you're using something like different bases, they're all still equalities to each other, just different ways of expressing the same thing. This is why I get pissed when people are like, well, 0.9 and repeating does not equal 1. Well, it's 1. It's just a different way of expressing it. I
Right,
don't know why
exactly.
it's so
That's right.
confusing to people.
Yeah.
But anyways, thank you two for joining us. Again,
So,
I know a lot of people are not going to probably watch this video because it's math, and some people like it, some people don't. But I hope to give an overall basic overview of summations in a very, very simplistic way, just so it takes away some of the stigma when they look at that symbol and go, oh man, that's Greek. It's confusing. And maybe people have messaged me on other things they want to talk about. They want me to explain some pre-calc stuff. They want to explain wave functions, and that's going to be fun. Right. I actually think wave function is going to be really cool. So Jonathan, promote your channel real quick. We got to get you like to 1,000 subs.
Yeah, that'll be awesome. So it's Epic Math Time, which is a name I'm very proud of. But yeah, I work a lot of problems in a very, very visible format. I just write kind of in front of me, and I'm try to be very clear, and I tackle some interesting problems that don't require a lot of background. That's up right now. I'm gonna do more stuff later, but I think next video I'm gonna talk about the different types of infinity. So maybe people like that.
Ooh, like absolute infinities and things of that nature.
So the uncountably infinite and countably infinite, and there's actually ways to get even larger infinities by something called Cantor's theorem. But
oh, that's gonna be
cool
that's be
cool
fun.
Stuff. Yeah,
that stuff I gotta admit, even to this day,
orders of infinity are fun.
Yeah, cardinalities. If you can do something on cardinalities, man, I watched that video a couple times, especially.
Oh yeah, I'll do it. I'll do it. You've inspired me. I'll do it tomorrow.
Awesome.
All right, say well, and Steve, again, thank you very much for all the hard work you're doing. This guy is one of the hardest working guys on YouTube. You do amazing set of stuff. So go ahead and subscribe to Steve and check out. And thank you again for having shows where not everything is a dumpster fire.
I try to, I appreciate that. I try to have a combination of both. I know Kyle loves the dumpster fires, and I'm not gonna say that I don't appreciate them, but I like to learn stuff, and I like to be able to share stuff with people so they understand it. Again, I am a complete layperson. Please, dear God, do not treat me as an expert on anything. I am not. Even though I had a lot of physics training and math training, that was decades ago, and I never pursued it afterwards. So I didn't, become well versed in any of the stuff. But my whole goal is if I can explain it to somebody and I understand it well enough, then I'm hoping that even the most amateurist person can understand it. That's the goal. That's it. I want to take the stigma out of this stuff, because a lot of the stuff is not as complicated as people make it out to be, and save that for the actual complicated stuff. But anyways, we're going to be going over to the Non Sequitur show now. Go check it out. You guys both can go over and watch it as well if you want to see flat earthers get destroyed. That'll be starting in a few minutes. So
I will be going and doing some good stuff. I'm besides some technical things, I'm also doing my backups. Hopefully everyone does their backups. Have you done your backups lately?
Have you done your backups today?
It's the equivalent of flossing for data science.
Yeah, I'm glad you mentioned that, because I probably should, because I had an old laptop crash where I had some data on there I wish I would have kept, and I'm still trying to salvage it. But yeah, backups are important. So here you go. Do your backups. We'll leave you at that. Word of advice for the day.